Precision is everything. Seriously, when you're operating in the high-stakes battleground of advanced mathematics, approximations just won't cut it. Today, we're leaving close enough in the dust and stepping right into the realm of absolute certainty. Welcome back, future doctors, engineers, and focus learners. So, you think you know limits? Well, think about this. When SpaceX is designing a heat shield for atmospheric reentry, close enough is literally a fatal mistake. You can't just guess the temperature. You need the exact mathematical limit of that thermal tolerance. Today, we're taking the beautiful, dynamic logic of James Stewart's calculus, the mathematics of change and motion, and applying it to exact, real-world problems. We're going to bridge that gap between pure theory and physical reality. You ready for a new mathematical thrill? Let's get into it. Okay, here is today's Boss Rush agenda. We've got limits versus real engineering, problem 1, the velocity siege, problem 2, the algebraic rescue, a fun little section called Lies My Calculator Told Me, problem 3, the boss fight, and finally, the final math challenge. Section 1, limits versus real engineering. Let's look at the dynamic logic of calculus. But hey, before we hit the first level of our mathematical battleground, I've got to give a huge shout out to our Calculus Heroes leaderboard winner. You totally proved your mastery and dropped the fastest correct answer to our last challenge right there in the comments. Your logic was absolutely flawless. Now the question is, who's going to clean the top spot today? Moving on to Section 2, Problem 1, which I call the velocity siege. We're talking secants and tangents here. For our first challenge, we've got a classic applied physics problem. Imagine a rock is thrown straight up on the planet Mars. Its height in meters after t seconds is given by the equation y equals 10t minus 1.86 t squared. Now, we need to find the instantaneous velocity of that rock at exactly 1 second. You see, finding an average velocity over a stretch of time, that's pretty easy. But finding it at one specific, frozen instant, well, that requires the magic of a limit. Now notice how mathematically shrinking our interval actually forces us toward our exact speed. What we do is calculate the average velocities over smaller and smaller time intervals. We start with a window from 1 to 1.1 seconds. Then we squeeze it tighter, looking at 1 to 1.01 seconds. As the difference in time, which we call h, gets closer and closer to 0, the slopes of these secant lines are mathematically converging toward the exact slope of the tangent line. It's like zeroing in with a microscope. And boom, there is our answer. The average velocities lock in on a limit of exactly 6.28 meters per second. By taking the limit as h approaches 0, we didn't just make an educated guess. No, we proved the exact speed of that rock at that precise millisecond in time. Actually, pause the explainer for just a second and think about this. If we calculated the velocity at the exact peak of the rock's flight, right before it changes direction and falls back to the Martian surface, what do you think the limit would be? Really think about the tangent line at the very top of a parabola. Got your guess? Well, it would be exactly 0. The rock literally stops for an infinitesimal moment before gravity pulls it back down. Kind of wild to think about, right? All right, Section 3, Problem 2, the algebraic rescue. Time to deal with indeterminate forms. We're leveling up here to a complex limit where just plugging in numbers is going to fail us completely. If we try to evaluate the limit as t approaches 0 for our expression, that's the square root of t squared plus 9 minus 3 all over t squared, direct substitution gives us the dreaded 0 over 0. That's what we call an indeterminate form. Basically, it means the limit might actually exist, but our current algebra just isn't revealing it. So we've got to deploy the rationalization trick. We do this by multiplying the top and bottom by the conjugate, which is the square root of t squared plus 9 plus 3. And as you multiply it out, something awesome happens. The t squared terms beautifully cancel each other out from both the numerator and the denominator. We are no longer dividing by 0. So we plug in our 0 and we're left with exactly 1/6, locked in perfectly. We literally just used math to bypass a hole in the graph. Moving to Section 4, Lies My Calculator Told Me. It's machine versus math. Listen, you've got to be careful here. If you try to find the limit of the sine of pi over x as x approaches 0 using a calculator's data table, it's just going to spit out a series of zeros. It looks incredibly confident, right? If you plug in 0.1, 0.01, 0.001, the sine of any multiple of 10 pi is just 0. But James Stewart's rigor reveals the actual mathematical truth. If you look at the true behavior of the graph near 0, It doesn't approach a single number at all. It's this wild, undefined oscillation bouncing infinitely fast between 1 and -1. The calculator was blindly sampling points that just happened to cross the x-axis. This is exactly why human logic and rigorous calculus will always triumph over a machine's blind calculations.
Section 5, Problem 3, the boss fight. Enter the epsilon delta proofs.
All right, it's time to stop calculating and start proving. To truly prove the limit of 4x minus 5 equals 7 as x approaches 3, we have to establish a watertight, guaranteed relationship between our inputs and outputs. In the formal definition, for every epsilon greater than 0, there must exist a delta greater than 0. By setting up the inequality, the algebra simplifies to show that our distance on the x-axis, which is our delta, must be exactly epsilon divided by 4. So what does this actually mean in the real world? It means absolute engineering certainty. If a manufacturer demands an output tolerance, or epsilon, of 0.01 millimeters, we mathematically know for sure that we must control our input machine precision, or delta, to within 0.0025 millimeters. Precision isn't guessed, it's guaranteed by proof. Finally, Section 6, the final math challenge. Let's tackle the difference of powers. Okay, you've survived the battleground. You've beaten the epsilon delta boss. But now it's time to face this massive, seriously intimidating 1,000-degree limit. Here it is, the limit as x approaches 1 of x minus 1, all divided by x to the power of 1,000 minus 1. I want you to use your factoring skills, specifically the difference of powers, to solve this completely by hand without a machine. Once you figure out the exact fraction, drop your result in the comments to claim your spot as a calculus hero. And hey, to help you along the way, make sure to grab your branded PDF cheat sheet from the link below so you can master these limit rules and algebraic tricks offline. Keep that logic sharp, and I'll see you right back here for our next explainer as we tackle the wild concept of continuity. But until then, I want you to ask yourself this. If calculus allows us to literally tame the infinite, what limits exist on your own potential? See you next time.